Let's talk about the fundamental theorem of Galois theory. So I'll start with this example. We'll use this to illustrate the first part of the theorem. It's the splitting field of this polynomial x cubed minus 2 over rational numbers. The polynomial x cubed minus 2 factors like this in complex numbers. So here are the three roots. Call them alpha 1, alpha 2, alpha 3. You add those three roots to rational numbers and you get this field L, which you can also get just by adding a cube root of 1, e to the 2 pi I over 3, and a cube root of 2. This is a degree 6 Galois extension. We have seen that already. It's a splitting field extension, and we are in characteristic 0, so all finite extensions are separable. So this is Galois with Galois group S3. We didn't quite prove that, but I claim that's so. We know that it's a degree 6 extension. Put the group S3 here, and I've written down all its subgroups. There are 6 subgroups, S3 itself, 4 proper subgroups that are different from the trivial subgroup and the trivial subgroup. And the arrows indicate which is contained in which. In this side, as you go down, things get bigger. And on the left-hand side, I've written down the subfields of L that contain Q. There's L itself, there's Q, and there are 4 sub-intermediate fields that are properly in between. And as you can see, there is a clear correspondence between these. And the first part of the Galois theory fundamental theorem establishes this correspondence, that there is a one-to-one order reversing correspondence between the subgroups of this Galois group and fields that are in between L and Q. If you give me a subgroup, say H, I can look at its fixed field, and that would give me the corresponding subfield, etc. So we'll revisit this again, but let's see how this works in general. Let's take so I want to explain how you get this correspondence between the left-hand side picture and the right-hand side picture. So take some finite Galois extension L over F with Galois group G. So I'll write G for the Galois group. Need a one-to-one correspondence between fields that are in between L and F and subgroups of G. So you give me a field M that is in between L and F, and I have to produce a subgroup of this Galois group G. We know that if the big extension is Galois L over F, then the upper part L over M is also Galois. This we have seen before. I want to look at the Galois group of that part, L over M. What does it consist of? It consists of those automorphisms of L, by definition, that fix M pointwise. So whose restriction to M is identity. So these are automorphisms of L that fix M pointwise, so they certainly fix F pointwise, because F is a subfield of M. So by definition of Gal L over F, these automorphisms, sigma, are in Gal L over F. So Gal L over M is a subgroup of Gal L over F. So rather than writing the subset like this, we'll put a hook arrow to show inclusion. So again, on the group theory side, as you go down, things get bigger. And on the field theory side, as you go up, things get bigger. So F is included in M is included in L. And similarly, L corresponds to Galois of L over L, which means automorphisms of L that fix L pointwise. There's only one such automorphism, the trivial automorphism. So this is just the trivial subgroup. That's one arrow. You gave me a subfield, I gave you a subgroup of the Galois group. Let's call that phi. Oh, I want to call that gamma. On the other side, let's write this extension again. You give me a subgroup of the Galois group, and I have to produce a field in between L and F. Well, I'm just going to look at the fixed field. Means all elements of L that are fixed by every element of the subgroup H. That's certainly a subfield of L. And every element of H is an element of G, so they fix F pointwise. So it contains F. So it is an intermediate subfield. And that's the other arrow. Let's call that phi. The claim is that this gamma and this phi, going from subfields to subgroups and going from subgroups to subfields, are inverse bijection. So they set up a one-to-one correspondence between the subfields of L containing F and the subgroups of G. That's part A. And how do you check that? Well, you apply these correspondences back to back. Let's start with a M, a subfield between L and F, and apply the two arrows back to back. When you apply the arrow that takes you from subfields to subgroups, you get to this subgroup Galois L over M. Let's call that guy J. Then L over M is Galois with Galois group J. And then if you apply the other arrow, you are supposed to look at L upper J, the fixed field of J. Well, I'll remind you of this lemma. This we have done a while ago. If you have a finite Galois extension L over M, this corresponds to that, with Galois group J, then L upper J is just M. So this is just M again. So if you start with M, go to the subgroup and take the subfield corresponding to that subgroup, you just get the subfield that you started with. That's rather straightforward. On the other hand, you start with a subgroup H, subgroup of G, take the corresponding subfield. Now look, H is a subgroup of the Galois group. So H is a finite subgroup of automorphisms of this field L. And Artin's theorem, our big result last time, showed that when you take a finite subgroup of automorphisms of a field and look at this extension L over LH, this is Galois. This is by Artin's theorem. This was a non-trivial argument. So because this is Galois, it makes sense now to apply the other arrow, gamma, and go to Galois L over LH. But Artin's theorem also says that that Galois group is just H. But when we go to L over LH, its Galois group is exactly H. So that tells you that if you start with a subgroup, look at the corresponding subfield, and then look at the subgroup that corresponds to that subfield, you get back to the subgroup H that you started with. That tells you now that these correspondences, gamma and phi, when you apply them back to back in either order, you get back to where you started from. So they are inverses of each other. So this sets up a one-to-one correspondence. What about the inclusion reversing part? Well, that's basically just group theory. I mean, if you take a H prime, some subgroup that is smaller than H. Remember, in the group theory side, as you go down, things get bigger. So when I'm up, I'm even smaller. Then a smaller subgroup is gonna fix at least this much. Probably it will fix more. So that's why you get a subfield that is bigger, and vice versa. So that gives you part A. Part B is literally the statement of Artin's theorem, that when you take a subgroup and look at the extension L over LH, that's Galois with Galois group H. So the upper part of this extension is always Galois. The lower part is not always Galois. By the way, by part A, now we know that any intermediate field between L and F looks like this. Looks like L upper H for some H, for some subgroup H of G. This lower part is not always Galois, but part C says that it is Galois if and only if this H is a normal subgroup of G. And if it is Galois, then what's the Galois group? Well, you can guess. It's going to be G mod H. And we won't prove this. The proof is nice, though. You can look in the notes. Okay. So So this sets up this beautiful correspondence between the field theory side and the group theory side, which can be exploited in both directions, but in particular, in number theory, this has huge implications because you can calculate lots of things on the field theory side, or solving polynomial equations, that sort of thing, using group theory. And this is called the original Galois correspondence. And similar bijections between two walls, similar inclusion reversing bijections, have shown up since many times in different branches of mathematics, and they're all called Galois correspondences, and they're often very useful gadgets. Let me end with looking back at this example. Well, if you give me an element 1, 2, 3 of the permutation group, how does it act on L? It permutes the roots alpha 1, alpha 2, alpha 3, as you would guess, sends alpha 1 to alpha 2, alpha 2 to alpha 3, alpha 3 to alpha 1. In fact, we did actually construct an automorphism of this Galois, automorphism of L, meaning an element of the Galois group, that does exactly that. Similarly, you could construct an automorphism that switches alpha 2 and alpha 3, fixes alpha 1, fixes 2 to the 1/3, but switches these two. But actually I can cheat and I can tell you what this automorphism is. This is just complex conjugation. So note, complex conjugation is certainly an automorphism of complex numbers, but it fixes L because it fixes 2 to the 1/3 and takes omega to omega bar, which is omega square. So it fixes L, and what does it do? It fixes 2 to the 1/3 and it switches these two other roots, because this is just the complex conjugate of that. So this guy is just complex conjugation. So now what you have is that in the Galois group, you have two elements at least that act as 1, 2, 3 and 2, 3. That tells you, but these two things already generate a S3. So you get that S3 is sitting inside the Galois group. On the other hand, this extension, L over Q, is degree 6. So the Galois group has order 6. So that tells you that the Galois group has to be exactly S3 and nothing more. So now we know that this is Galois L over Q. Once you know that, you could work out quickly the subgroups of S3. There are 4 proper subgroups that are different from identity, generated by these permutations, and then there is the trivial subgroup. And for those, you can write down the fixed fields, and you get these fields. And then you get the conclusion that these are the only fields that are between L and Q. There's L, there's Q, and there are 4 things in the middle, and there is nothing else. If you try to prove this by hand directly using the field theory side only, I think you'd have to do quite a bit of work. That's the kind of thing that the fundamental theorem of Galois theory tells you. The group theory side here is kind of trivial, but it gives you something rather non-trivial on the field theory side. If you give me a subgroup here, here is, and the upper part is always Galois. So these are always Galois. If you take Lj, the Galois group here is J. But the lower part is not always Galois. It is Galois when the subgroup is normal, like this one is a normal subgroup. So then this part is actually Galois. So that's from part C. This is actually Galois. And the Galois group is S3 mod, the subgroup generated by 1, 2, 3, which is Z mod 2, which you can check directly. This is the splitting field of x squared plus x plus 1. If you want to really understand what's going on in this theorem, I strongly suggest that you work out a few more such examples. I've written out 3 more polynomials and their splitting fields. Work out the left-hand side of the picture and the right-hand side of the picture, and write down the correspondences, all the subgroups of the Galois group and the subfields in between these things, and then you'll see what's going on. It's quite beautiful. We could go on, of course, but we'll stop with this.